All right, this is section 8.4 over surface areas and volumes of similar figures, and this comes right off of talking about perimeter and area. So I just want to review that real quick because we have to understand that if we're going to move on from this and continue working on it. So perimeter, we said that the ratio of the side lengths is equal to the ratio of the perimeters. So and that the reason because they're equal is because perimeter is one-dimensional. It's a distance. So if you know the ratio of the distance of the side lengths, then you know the ratio of the distance around it, and they're equal. I just need to make sure I reduce. But area is two-dimensional. It's got a length and a width, right? Or a base and a height. So we square. So we take the ratio of the side lengths, we square it. So the ratio of the areas is equal to the square of the ratio of the side lengths. So take the side lengths, square it, you have your area ratio. So today when we talk about surface area, we're still going to do the same thing. We're going to pick up right where we left off because surface area is still two-dimensional. So if I put surface area in front of this, I do everything else the exact same way. It's still two-dimensional, so I'm still going to square my side length ratio. And then I want you to think, what would you do you think, for volume? Think about when you find the volume, how do you label your units then? We'll come back to that here in a moment. So, surface area. As we just mentioned, when two solids are similar, the ratio of the surface areas is equal to the square of the ratio of their corresponding side lengths. So just like before, this is going to be a complete review. If I know A is 3 and I know B is 8, then I use 3, 8, which is my side length slash perimeter ratio, which I guess we don't really have perimeter for three-dimensional shapes. And then I square that, and that would give me 9/64ths for my area ratio. So that's what I'm doing again today to find the area ratio. So this says find the two perimeters are similar, two pyramids are similar. What is the surface area of pyramid A? So what we're going to need is we're going to need that surface area ratio, and then we will apply it. We will actually get to use it. So I know it's 6/10, which reduces to 3/5. So the side length ratio is 3/5. And I know for area, I have to square that. So that's going to give me 9/25. So the area ratio is 9/25, right? So now I can use that area ratio and find a missing dimension. I don't know the surface area of the pyramid, but I do know the surface area of the red pyramid, but I do know the surface area of the blue pyramid is 600, and I'm just going to cross multiply. So 9 times 600 is 5,400 divided by 25 is 216. So I did 25 times S. I did 9 times 600. I divided and got 216, and that's going to be feet squared. And technically, that should be red because that's the red pyramid. So that is the surface area for the pyramid, the red pyramid there. Let's see if we can do that for these two shapes here. Again, it's giving us the surface area of one of them. We have to find the missing surface area of the other one, but we don't have any other dimensions. We don't need them because we know the figures are similar. That is the dead giveaway here. They are similar. So if they're similar, then I know the ratio of their corresponding side lengths would be 8/5. And then I know if I'm supposed to square the side length ratio, that gives me 64/25. So then I'm going to use that ratio 64/25 and make a new proportion. The 64 represents the first prism, and I know the surface area of the first prism is 608, and the 25 represents the surface area of the second prism, which I don't know. So I'm going to cross multiply. 608 times 25 is 15,200, and I'm going to divide that by 64. And that's going to give me 237.5, and this is meters squared. Okay, so there's 1. And then for the example B, the other one there, we've got a cylinder, but it doesn't matter what shape it is. I know that they are similar, so I know the side length ratio is 5:4, and I'm supposed to square that side length ratio, and that's going to give me 25/16. And then I'm going to create a new proportion. 25/16 is equal to, I don't know the surface area of this one. I do know the surface area of this one is 110. So 25 times 110 is 2,750 divided by 16 to cross multiply. We get 171.875, or I guess I could round it to 88 centimeters squared. All right, so for volume, this is the new one, but it's actually not that new. You may have already thought about this, but when two solids are similar, the ratio of their, should say volumes, sorry, that's a typo. The ratio of their volumes is equal to the cube of the ratio of their corresponding side lengths, because for volume is three-dimensional. So we're going to cube the corresponding side lengths to get our ratio. All right, so our side length ratio for these two cones is 5:12 using the heights of the cones. I know they're similar, so I know those heights are proportional, so 5:12. And then I am going to cube this ratio because I'm using volume. So 5 times 5 times 5 is 125, and 12 to the third power is 1,728. So I'm going to create a new ratio. I'll just write it off to the side here, a new proportion. I don't know the volume of the first cone, but I know the volume of the second one is 288. So I'm going to cross multiply. I'm going to do 125 times, cross multiply here, times 288, 36,000, and I'm going to divide by 1728, and we get 20.83 repeating, and that would be centimeters cubed, and that is the volume of this cone right there. And then for example B, my side length ratio, you can see they're giving me 3 and 4. And that's my side length ratio, so I'm going to cube it, and that's going to give me 9 over, I'm sorry, not 9, I'm squaring. Let me back up. That's going to give me 27 over 4 times 4 times 4 is 64, 4 cubed. So I'm going to use that new ratio or proportion. I don't know the volume of the red one, but I do know the volume of the blue one, and the blue one is the first one I'm going to write, which is 9, and the volume of the red one is unknown, so there's my new proportion. I'm going to cross multiply 64 times 9 to get 576. I'm going to divide it by 27, and that's going to give me 21.3 repeating inches cubed. So now we know the volume of the red pyramid. And for our last example here, it says the dimensions of the touch tank at an aquarium are doubled. What is the volume of the new touch tank? So they are going to double all of the dimensions, and if they double all the dimensions, we know that's going to not just double the volume. In fact, if they double all the dimensions, if we raise that to the third power, we know that is going to multiply all of them by 2 times 2 times 2, which is 8. So it's going to have an effect of timesing the volume by 8. And 2,000 times 8 is 16,000 feet squared. So you can see the study tip over here. When the dimensions of a solid are multiplied by k, which in this case our k was 2, right? The surface area is multiplied by k squared. That makes sense. Surface area, square units. And the volume, which we had for this problem, is multiplied by k to the third. So that's why we did 2 to the third, and that gives us 8. So when we double the dimensions, that's what we're saying. When we double the dimensions here, we're going to raise that to the third power. So doubling the dimensions means we're actually timesing by 8. And if we were tripling the dimensions, we would end up timesing everything by 27. You can see that's kind of what the study tip there is saying. All right, that's the end of this section. Let me know if you have any questions.